Now we come to titrations. What a titration is it's an analytical technique. Let's say we wanted to know the concentration of this solution. We didn't already know it. We have a technique, a way to measure that concentration. So it's just a technique that we use to determine the concentration of one solution that's unknown by using the solution of known concentration, and we call that a standard. It's essentially our ruler, our measuring device. It's just a solution of known concentration. The equivalence point, the point at which stoichiometrically equivalent amounts or quantities are mixed. So you remember stoichiometry. Let's say I were adding sodium hydroxide to H2SO4. The equivalence point has been achieved when I have stoichiometrically equivalent amounts of my reactants are mixed. That's what we mean by the equivalence point. So here we have a strong acid, strong base reaction producing two products, sodium chloride and water. In order to know when we're close to the equivalence point, we need to add an indicator, which is just a colored dye that changes color when we approach a particular point in the titration, presumably close to the equivalence point. And it's going to produce a color change. And we call that color change the end point of the titration. To know precisely when the equivalence point was, we would need to be able to view the reaction on the atomic molecular level. So you might think of the end point as being sort of a crude representation of that, but it is the point at which the indicator changes color, and that signals the end of our titration. So this is the way our setup looks. We've got an Erlenmeyer flask here. We're going to put in a very precise amount of what's to be titrated. And so once we get this in there, and we're saying that we're going to have 20 milliliters of whatever it is we're titrating. This is probably the unknown concentration of some acid. It could be a base, it could be some other type of titration, but we know what our volume is to a reasonable degree of precision. And then what we're going to do is we add an indicator. You have to put an indicator into the solution in order to get your color change as you get close to the end point of your titration. So you have an indicator. Now this is a burette, and it typically holds 50 milliliters of your titrant, what you are adding to the solution to be titrated. And this you know to a high degree of certainty. Let's say we know this is something like 0.1014 molar. So we know the concentration of our standard. This is our standard. This is what we're using to measure. And because we know the concentration to a high degree of precision, a low degree of uncertainty, now when we start adding this to the solution and we get to the end point, so this is a color change, and this would be the end point of our titration, we can take a volume reading. We'll have a final volume and an initial volume. The initial volume will start out at 0.00 milliliters. The final volume, let's say this is 45.00 milliliters. We know we added 45 milliliters. And we're going to be able to use that to determine what the original concentration that we started with of this solution is. And that's because volume times the molarity, which is moles over volume, is equal to moles, and that's because as long as the volumes are in the same units, they will cancel, and that's going to give us a unit called moles. That tells us how many moles there were at the start of the titration of, let's say, our unknown acid, our unknown base, or whatever it is we're titrating. And from that and the volume that we started with, we can compute the concentration. And that's how a titration works. This is what it looks like. Our titrant is up here in the burette. We have a stopcock. In here we have what's to be titrated and an indicator. And the reason we want the indicator in there is so we get a color change. So typically you'll open up the stopcock and you will simply run your titrant, your standard, into the solution pretty freely. As soon as you get a local color change, you stop just running it in and you go to drop by drop, because you're going to be close to the end point of the titration. And you continue the titration until you get that persistent color change, and then you are done and you can do your calculations. All right, here is a titration problem which describes a particular situation. Let's see where we are. So this says how many milliliters of 0.2 molar acetic acid solution is required to neutralize 50 milliliters of 0.0875 molar sodium hydroxide. So let's set the situation up so that we can get some kind of visualization of what we're dealing with. I know that's not the prettiest burette in the world, but I never claim to be an artist. Okay, so here's your Erlenmeyer flask. Down here in the Erlenmeyer flask, you have 50 milliliters of NaOH, and we even know in this particular case that the concentration of the NaOH is 0.0875 molar. And we're asking a little bit of a strange question. We're asking how many milliliters of 0.200 molar. This is acetic acid, HC2H3O2. I'm going to have to add in milliliters to get to the end point of the titration, to get to a color change. So let's set up our problem, and we can set the problem up in a couple of different ways. The first thing we need is a balanced chemical equation. So here is acetic acid, HC2H3O2. It's given in the problem. And we're using sodium hydroxide, NaOH. This is an acid-base neutralization reaction. Acetic acid is actually a weak acid, and this is a strong base. We are going to get a salt and water from this. This is a neutralization reaction. We know it as a metathesis reaction, where the sodium is going to glom on to the acetate. The hydrogen ion will grab a hold of the hydroxide. So we'll get NaC2H3O2 plus good old H2O, our driving force for this particular reaction. So here's what we have in our metathesis reaction. We've got 0.200 molar of the acetic acid. We want to know how many milliliters of it are going to be required to neutralize a concentration of 0.0875 molar sodium hydroxide, and we have 50 milliliters of the stuff. This is a little bit different because we've got the sodium hydroxide in the Erlenmeyer flask. We're adding the acid, the weak acid, to this concentration of sodium hydroxide. So that's a little bit different, but nevertheless, the math will all work out. There are two ways to do this based on the stoichiometry of the balanced chemical reaction. So let's do the first method. So that's going to be X milliliters, and in this case of HC2H3O2 is equal, and what goes on the other side of the equal sign is the volume of the other stuff, because remember, we're operating on the principle that volume times molarity will give us moles. So this is going to be 50.00 milliliters, and remembering this is the NaOH, we're going to go ahead and convert milliliters to liters by dividing by 1,000. So 1 liter is equal to 1,000 milliliters, and then this is 1 liter of, and you have to remember this is the sodium hydroxide, and it's got a concentration of 0.0875 moles for every 1 liter. This is the molarity, moles over liters. So this symbol, molarity, is equal to moles over liters, and we've represented that molarity here with moles over liters. A lot of people make the mistake, they'll put the capital M up there. This is moles over liters. So this is NaOH. Then we have to go to the mole to mole ratio. Well, the mole to mole ratio in this reaction is 1 to 1. So this is for every 1 mole of NaOH, we require 1 mole of the acetic acid. And that's because acetic acid is monoprotic. Okay? There's 1 mole of hydrogen ion for every 1 mole of hydroxide ion in this reaction. And then we have a concentration of 0.200 molar acetic acid, so that'll be 0.200 moles of acetic acid, HC2H3O2, for every 1 liter, and then finally every 1 liter is equivalent to 1,000 milliliters, and that is our X factor for this reaction. Now we'll just make sure that our units cancel. I have milliliters of sodium hydroxide over milliliters of sodium hydroxide, liters of sodium hydroxide over liters of sodium hydroxide, moles of sodium hydroxide over moles of sodium hydroxide, moles of acetic acid over moles of acetic acid cancel, and liters of acetic acid over liters of acetic acid. That gives me my X factor, which is X milliliters. This is the acetic acid. And so once I plug this into the calculator, that will give me the milliliters of acetic acid that are required to neutralize 50 milliliters of 0.0875 molar sodium hydroxide. Now you'll note in putting in your calculator, you've got 1,000 milliliters of sodium hydroxide down here in the denominator and 1,000 milliliters of acetic acid up here in the numerator. Mathematically, those two would just cancel each other, so you don't need to put that in your calculator. You can, but it's unnecessary. You can just multiply 50 times 0.0875 divided by 0.2, and that's all it's going to take to get the answer. So that's just going to be 50 times 0.0875 divided by 0.2, and that gives me 21. Let's see, how many sig figs are we going to have? Well, I've got 3 sig figs in my concentration here, 3 sig figs here. So that's going to give me 3 sig figs in my answer. So that will be 21.9 milliliters of the acetic acid HC2H3O2. Now, there is another way to do a titration problem, and I want you to take a look at this. Let's take a look at HC2H3O2. 3O2. And over here, I'm going to give you sodium hydroxide. Now, if I were to ask you whether acetic acid is monoprotic, diprotic, or triprotic, you would look at that leading hydrogen. That's how you're going to tell whether an acid, in this course at least, is mono, di, or triprotic. And the subscript is 1, so you know this is a monoprotic acid. It really only has one proton, one acidic proton to donate to the reaction. I'm going to look at sodium hydroxide over here, and now I'm just focused on the hydroxide. And I'm going to use a similar term. I'm going to say, is this a monohydroxide base? That is, for every 1 mole of sodium hydroxide, how many moles of hydroxide are available to be donated? And that answer is 1. So if this were to dissociate, it would dissociate into 1 mole of sodium cation, 1 mole of hydroxide ion. So here is the equation we can use to solve the problem a little bit more simply. We can say how many moles of hydrogen ion are available to be donated per mole of the acetic acid times the molarity of the acid, and I'm just going to use HA for acetic acid. The HA is just a generic acid, and then times the volume of the acetic acid, and that's going to be stoichiometrically equivalent to the number of moles of hydroxide ion that are available per mole of the sodium hydroxide. And here I have the molarity of the sodium hydroxide times the volume of the sodium hydroxide. And if you remember, volume times molarity equals moles. Volume times molarity equals moles. So if I put the right values for everything in here, let's see what my result is. So I've already determined this is a monoprotic acid, so the number of moles of hydrogen ion available per mole of acetic acid is 1. The number of the concentration of the acetic acid that's given in the problem is 0.200 molar. And then the volume of the acetic acid, well, that's what we're looking for. We're looking for X milliliters of the acetic acid. Now, let's look at the sodium hydroxide. For every 1 mole of sodium hydroxide, we get 1 mole of hydroxide ion. So that's also going to be 1. And the molarity of the sodium hydroxide that's given is 0.00875 molar, and the volume of the sodium hydroxide is 50.00 milliliters. Working the problem this way, solving for the number of milliliters of acetic acid, I would simply divide both sides by 1 times 0.200 molar, and over here those will cancel. I'm going to do the same thing on this side of the expression. 1 times 0.200 molar. When I do that, the ones, obviously, those cancel. I have 0.0875 molar times 50 divided by 0.2. All right, let's take a look at the math in the method above. I have 50 in the numerator, 50 in the numerator here. I have 0.0875 moles in the numerator. I have 0.0875 in the numerator. And then I have 0.2 in the denominator. Everything else either cancels, like the thousands, or is 1. So the math is the same, and so I will come out with the same answer, which is 21.9 milliliters of my acetic acid. Now I want to caution you, this is not the dilution formula. This is a method for doing titrations. It looks like the dilution formula because you have molarity times volume equals molarity times volume. If this is not a monoprotic acid, or this is not a monohydroxide base, and you use the dilution formula, you will get this problem incorrect. You will get it wrong. All right, so let's choose a problem in a titration where that's the case. So here we have 26.35 milliliters of standard sodium hydroxide, which is 0.1650 molar. We know that concentration. And it's required to neutralize 35 milliliters of H2SO4. What is the molarity of the acid solution? So this is a more typical titration problem. We're looking for an unknown concentration. Let's go ahead and let's take a look at exactly what is going on physically. So here is our burette. Here's our Erlenmeyer flask. The good thing about this on video is I can't hear you laughing, which is just fine with me. We're going to make sure, so what do we have down here? We have 35 milliliters of H2SO4. The concentration is unknown, so we have an unknown concentration, an unknown molarity. Now the other thing we need to make sure we put in here is an indicator. If you forget your indicator, and lots of people do, they go do their titrations and they wonder, why am I not getting to the end point? That's because they forgot to put the indicator into their solution. So don't be that person. Okay? We're going to add what we have. Let's see, what do we have in here? We've got sodium hydroxide. It's 0.1650 molar, and it takes 26.35 milliliters of adding this to our unknown sulfuric acid solution to get to the end point. And you remember that the end point is a color change, and it is approximating the equivalence point. So the first thing we need is we need a balanced chemical equation. Sodium hydroxide, and then this is a metathesis reaction, so the sodium is going to join the sulfate, the hydrogen ion is going to join the hydroxide and make water. So here's our salt. It's sodium sulfate. I need 2 sodiums because sulfate has a -2 charge. And let's go ahead and let's balance the reaction. I've got 2 sodiums here, so I need 2 sodiums here. I've got 1 sulfate, that's fine. I've got 2 hydrogen ions plus 2 times 1 hydrogen ion, that's 4. So I'm going to make 2 water molecules, 2 oxygens, and 2 times 1 is 2 oxygens. So I've obeyed the law of conservation of mass. This is my stoichiometrically balanced chemical reaction. All right, so let's use the stoichiometry method to solve our problem. We've got 35.00 milliliters of this stuff. We don't know what the concentration is in moles per liter. I've got it required 26.35 milliliters of sodium hydroxide, and that sodium hydroxide, that's our standard, that's our ruler, and it's 0.1650 molar. And so now we've added that, and now we need to calculate our concentration of our acid. How many moles of H2SO4 in there? All right, so what we want to know is X moles per liter of H2SO4. And so we start out with the volume of the other stuff. That's our titrant, the sodium hydroxide. So that's going to be 26.35 milliliters of the NaOH. We're going to go ahead and convert milliliters to liters, and 1,000 milliliters are in every 1 liter of the sodium hydroxide. The concentration of our sodium hydroxide is 0.1650 moles. And remember, this is the NaOH. For my money, you should label everything. Now here's where things get different. The mole-to-mole ratio is 2 to 1. 2 moles of sodium hydroxide are required to neutralize 1 mole of sulfuric acid. So that's going to be 2 moles of NaOH for every 1 mole of H2SO4. 26.35 milliliters times 1 divided by 1,000 milliliters. Milliliters cancels, and then liters over liters cancels. Moles of sodium hydroxide over moles of sodium hydroxide cancel. You wind up with 2.17 times 10 to the minus 3 moles of H2SO4. We want to get this into moles per liter, so we're going to go ahead and we'll divide by the 35.00 milliliters of H2SO4, and we'll go ahead and convert that to liters by dividing by 1,000 milliliters per liter. So when we've done that, we're going to get a concentration of the H2SO4 of 0.06211 capital M moles per liter. This is the H2SO4. Okay, that is the concentration of H2SO4 that was originally, before we began our titration, in the Erlenmeyer flask. So now that I've shown you the stoichiometric method for solving that, let's take a look at the other method. This is NH plus times the molarity, and I'll go ahead and write the H2SO4 times the volume of the H2SO4 is equivalent to the number of moles of hydroxide ion per mole of the sodium hydroxide times the molarity of the sodium hydroxide times the volume of the sodium hydroxide. All right, so here's H2SO4, here's the sodium hydroxide. And this is what you have to pay attention to. This is why this is not the dilution formula. This is a way of doing titrations, but you're acknowledging how many protons each mole or each molecule of your acid and each molecule or mole of your base have to contribute to this particular reaction. And that will be reflected in the lowercase n. This stands for moles of protons. This is what this means per mole of the acid. Well, this is a diprotic acid. That means for every 1 mole or 1 molecule of this, you get 2 hydrogen ions. So in this case, this would be 2. The molarity of the H2SO4 is what we are interested in this problem. The volume of the H2SO4 is 35.00 milliliters. Equals, we look at the sodium hydroxide. This is a monohydroxide base. That is, every 1 mole of this base has 1 mole of hydroxide. If you dissociate this, you just get 1. And so that means that the number of moles of hydroxide per mole of base is 1. The molarity of the sodium hydroxide, which is our standard, is 0.1650 molar. The volume of the sodium hydroxide given in the problem is 26.35 milliliters. We are solving for the molarity of the H2SO4, so we divide. We divide by 2 times 35.00 milliliters. We divide both sides by the exact same quantity, 2 times 35.00 milliliters. The 35 milliliters and the 2 cancels over here, and we solve for the molarity of the H2SO4. So we got 1 times 0.1650 molar sodium hydroxide concentration times 26.35. These are in the numerator. Well, they are also in the numerator in this particular method. The 2 from the mole to mole ratio is in the denominator here. The 2 from the fact that this is a diprotic acid. That's why the mole to mole ratio is what it is because this is a diprotic acid and this is a monohydroxide base. That's why that 2 is in the denominator, and then the volume of the H2SO4 is down here in the denominator, and in this problem the volume is in the denominator. So you will wind up with exactly the same answer using this method of calculating your titrations. All right, now I've got to emphasize this. I can't emphasize this enough. This is not the dilution formula. It capitalizes on a similarity in calculation, which is volume times molarity equals moles. But if you neglect the number of moles of H plus or the number of moles of hydroxide per mole of your base or per mole of your acid, you will get this problem wrong. Okay? Not the dilution formula. You can use either method. They both work absolutely beautifully. It is your choice. Last slide in chapter 4. What is the total concentration of ions in a solution of 0.5 molar barium hydroxide? Well, think of bicycles. This is a bicycle. And if I have a bicycle, let's see, boom, it's got a seat. Okay, there's the seat, there's the handlebars right there. And I take it apart, I get 1 seat, I get 1 frame. Okay, here's your frame. And I get 1 set of handlebars, but I get 2 of the wheels. All right, so barium hydroxide is just a bicycle. It's a dihydroxide type of base. So when I put this strong base into good old H2O, I wind up with 1 mole of barium in aqueous solution. I wind up with 2 moles of hydroxide in aqueous solution, assuming that we have complete dissociation. If this is 0.500 molar, then this will be, it's a 1 for 1, so the barium ion will be 0.500 0.500 molar. But I'll have 2 times 0.500 molar of the hydroxide ion. Well, 2.5 is going to be 1 molar, and then I have 0.500 molar here, and so I'm just going to add them up. Add those two up, and you get 1.50 molar if what we're talking about are ions. This is an ion. This is an ion, and it's 2 for 1. So our concentration of ions, what we call our total ionic concentration, is equal to 1.50 molar. In this particular case, we don't care whether we're talking about hydroxide ion or barium ion. We're talking about the entire ionic concentration. And so it's 1.50 molar.